Okay, that's the top of the hour, so I guess we'll get started. I see there's a good amount of attendees here already, and I think probably more will join us as we go. So, all right, welcome back, everyone, to Understanding Understanding Latency 3.0. My name is Bjørn Ivar Teigen Moncler. I'm head of research at Domos, and I will be your host. The previous Understanding Latency event was almost exactly 1 year ago. And over the next 3 days, we will hear what's happened in the internet latency space over the previous 12 months from a truly excellent group of industry experts. If you are curious about what was covered at one of the previous events, you can find the full recordings on YouTube. So first, let's get the practical details out of the way. This will be a knowledge sharing event. The point is to share experience, insights, and best practices related to measuring and improving latency. This is about highlighting latency-related challenges that all of us have a shared interest in tackling in the best way possible. We will have a series of talks every day. Each talk is 15 minutes. After each talk, if there is time, we will do a live Q&A. And for that, we invite everyone to ask questions. And to ask a question, please use the built-in Q&A system that you will find on the bottom of your screen in the Zoom tools. And please note that the webinar is being recorded, so questions and answers will be part of the published recording. The recordings will be published on YouTube, and we will share a link to those by email to everyone who's signed up for this event. And similarly with the slides, we will also make the slides available. So this is the agenda for today. I will do a short introduction, and then we have Gino Dion from Nokia, Jason Livingood from Comcast, Magnus Olden from Domos, Craig Thomas from the Broadband Forum, Benoit Claes from Huawei, Dan Seaman from Eterlo, and Professor William Webb. Tomorrow, Dave Todd from the Buffer Project and LibreQoS, Greg White from Cable Labs, Stuart Cheshire from Apple, Neil Cardwell from Google, Christian Anderson from Ericsson, and Simon Sundberg from Karlstad University. And then finally on Wednesday, we have Chesong Geng from Huawei, Dr. Madhan Raj Kanagarathinam from Samsung Research, Dean Bubley from Disruptive Analysis, Mayur Chanagauda from Vodafone, James Carroll from Ookla, and Koen de Schepper from Nokia Bell Labs. So first, I will do a short introduction. Latency 101 is the title of my talk. I will cover what is latency and why does it deserve all this attention. This will be sort of a high-level intro to network latency, just to make sure that everyone has a foundation to build on before we wade into more detailed topics. Okay. So in short, latency is just how long it takes to send a small amount of data from A to B. Usually, latency is measured by timing how long it takes to send a single packet. And the value you get is typically measured in milliseconds. 1 millisecond is 1,000th of a second. And for most internet users, their latency to like the internet, if that is something you can give a name like that, is about in the range of tens to maybe hundreds of milliseconds for the round trip to the internet. So if you measure from A to B and then back, so you just send a packet asking B to send a response, and then take the time. How long does it take to get a response? Usually for people, that's like tens to hundreds of milliseconds, which is pretty good. Honestly, it's amazingly good that you can send a message to almost anywhere in the world and get a response within literally the blink of an eye. It's amazing. And I think we all agree, or mostly agree, that best case internet latency like this is excellent. Um, so why are we having a 3-day webinar series about how to improve it if it's that good? And a very simple way to put that is that it comes down to this one word, competition. Without competition, there is really no problem. On an idle connection, if you're not competing with anyone else, usually you're going to have a good time. You're going to have a good connection on most technologies. But if you do have competition, then this kind of thing happens. And the competition is for resources. Like on the road with a car, the competition is like there can only be one car in any given space at any given time. So the cars have to be in different places and you form a queue. And it's similar on a lot of different internet technologies where if you want to send some data at the same time as someone else or some other application on your computer, or for some reason there's competition, then only one source or only one piece of data can be sent over the same time and frequency slot in a Wi-Fi network, for instance. So when there's competition, you get queues. And the way that we solve this in networks is to add literally a queue, a place to store data that has yet to be transmitted, because there is contention for the resource that is used to then transmit that packet. And these queues can cause delays of many, many times what your base or best case idle latency is. So these queues can be hundreds, if not thousands of milliseconds long. And at that point, you're starting to get problems with applications like video conferencing, gaming, web browsing, or pretty much any other use case that you have for your internet connection, um, will feel sluggish or frustrating when you get to those levels of latency. So poorly managed latency can have a very big impact on the perceived quality of an internet connection. And some use cases might be impossible if latency is not kept stable enough. So if we as an industry want to deliver things like reliable emergency response communications, or like teleoperation of robots, or even just stable, reliable video conferencing that you can trust, we need to fix the latency. And just to make sure that everyone understands that this is a current issue, let me um, throw one of Norway's biggest telcos under the bus a little bit. Um, I had new fiber installed in my apartment last week, in fact. And the first thing I did was, of course, to run a speed test. And as you can see, I have more than 500 megabits in both directions. Very good. Very happy with that. Um, but then there's this buffer bloat grade C, and this is not great. Um, this is this is the unloaded latency, 6 milliseconds. And then when there's a download happening, you have to add 157 milliseconds to that. And that is because of excess queuing in some place in the network. And because this test was actually run when I was connected, my desktop computer was connected via an Ethernet cable to the brand new Wi-Fi router. I believe this is somewhere in the fiber network, actually. Like there's some kind of rate limiter or something that is that has a queue that allows a queue to build up so that I get this extra latency. So this is not great. This is on a brand new fiber installation. And then when I connect to the Wi-Fi of the same router, I also get a C. Uh, Notice here that the speeds are lower, and that is just I walked far enough away from the router to make sure that the Wi-Fi is the bottleneck. So I didn't want to have more than 500 here. Um, but as we can see, again, idle latency is pretty good, 8 milliseconds, not bad at all. But with download or upload active, I get a lot more latency. And this is on a brand new Wi-Fi 6E router that I literally took out of the box on Wednesday. So um, this is a current problem. This is something that happens with new installations on with modern ISPs today. And just to add a little bit, 5G is not better than fiber here. So this is again, sorry to really shit on Telenor here, but um, this is a typical 5G link. I don't think Telenor is worse or better than anyone else, pretty much. The throughput is great. The ping on idle is great. Download and the upload ping times, or the ping times when there is a download or an upload, are not great. So we have a saying in Norwegian. No, you know what? I skipped a part. No, okay. So to be fair to Telenor, they are not the only telco getting this latency wrong. Delivering consistent low latency is hard because a single poorly configured step in the vast and complex end-to-end chain of technologies that deliver a digital experience like this can make the whole thing fail. And so we have a saying in Norwegian. I couldn't find a great translation for it, but it goes something like a small bump in the road can topple a big load. So there's something like this is happening. Most of the end-to-end network is probably working fine, but then there is some bottleneck somewhere where a queue is not managed properly, and that is causing the whole experience to be worse than it has to be. So fixing this problem involves improving technology on all levels of the network stack, from Wi-Fi contention algorithms to congestion control to where we physically locate the data that people typically access, to application level optimizations like replay buffers that smooth over dips in network performance. And that is what this webinar is about. It's about all of those different parts of our technology stack, um, pointing out the places where people have found performance problems and either measured them and they can report on some of the measurements, or have are working on solutions for how to fix those issues. So that is what we'll be spending the next 3 days doing, is covering these different topics with experts from across the internet industry, talking about the challenges and solutions that they are working on to improve how the internet works. So without further ado, let me introduce our first speaker of the day. That is Gino Dion. He is head of Nokia's Innovation Solutions team, and we'll be talking about the evolution of the broadband experience. So Gino, I will stop sharing and you can take over.
Yeah, of course. Thank you so much. Always excited and an honor to be with the crew and pedigree that you've assembled here at the Domus team. When I see people like Stuart and Jason, Craig, and everybody else that be participating, it's always incredibly exciting to see the attention that's been brought to this. And that got me thinking. There's a lot of different things I could talk about. Years of lab testings and results and things like that. And the funny thing is I know that a lot of the presenters will actually do that. So I decided to take a slightly different approach. What I'd like to do is actually talk about my personal experiences and some of the real world field results that we've got from different types of projects over the last couple of years. And I hope that will be interesting to people and help put into context all of the algorithms and bits and bytes that we're going to be talking about for the next couple of days here. So, all right, with that, when I look at the evolution of broadband services, it's very clear that things have to move beyond bandwidth. And I know it sounds sacrilegious. Somebody from Nokia saying, you got to look more than bandwidth because we offer 1 gig, 10 gig, 25, 50, and even prototype 100 gig on PON now. So why is it that people are still complaining about lag? People are still complaining about video conferencing, about streaming, and things like that. And the reality is that we've been focusing on the wrong things. We need to start looking at quality of service experience. And some of the work that Domos and many others have done around quality of outcome, KPIs is great. And the funny thing is once you start looking at that pillar, it starts pushing some very interesting benefits and attributes to the operators themselves and the ability to monetize things more than bandwidth. For the last 20 plus years, we've been selling, quote unquote, dumb pipes and, delivering the more bits for the less dollars. But that's got to change because people won't really care once you pass the 1 gig, 10 gig. What are the use cases out there on the internet that really make this worthwhile? There's not many, not in the residential context, at least. So what are the things that people value that are willing to pay for? And then finally, when you put these two things together, when you're able to measure the reliability and the performance of services and applications, and you're able to monetize it, it has a significant impact on the service assurance, on the quality of the service, the amount of time people will complain. You'll be replacing CPEs with no faults found all the time. So it all feeds into each other, and I thought it was really important to be able to bring those three things together. So the first thing is what is making some of this possible now? Why are we able to tackle all these things? And my personal view is we need to move from looking at that device in the home, that CPE, residential gateway, Wi-Fi box, whatever you want to call it, whatever you're using, from network demarcation to an edge computing device. And that's the number one key because it's funny, up to 5 years ago, and even today, but 5 years ago, I started seeing a slight change where for the longest time when Nokia were getting RFP requests from carriers asking us for an ONT or Wi-Fi box, it was always give me the cheapest thing that can deliver these minimum requirements because cost. It was the CPE was a big part of the business case, but that started changing a couple of years ago. We've started seeing some of the new entrants into the market asking for much more powerful devices, much more open devices, a lot more capabilities. So they started seeing that edge gateway not as a sunken cost, but as an asset, as a way to differentiate and to be able to move beyond just the battle for the speeds. And I thought that was really, really fun. And the broadband forum and a lot of different people have made some amazing capabilities available through these advancements in CPE technology, such as containerization and USB with managed apps and managed Wi-Fi and all of these things. And we're just starting to scratch the surface about what's possible and what's capable. But to me, the biggest reason why we're starting to be able to tackle the challenges and the issues that Domos has presented here is really the fact that now we have an edge compute device in the home that we can take advantage of. So again, instead of the bits and bytes, let me show you some real world examples about more faster bandwidth isn't always the answer here. I remember during COVID days, we had a lot of carriers reach out to us. Their networks were under stress, and they were trying to figure out how can I help the working from home community better. And often that was followed by the next question is, well, are people willing to pay for it? So I took advantage of some series of light reading webinars and other things I was doing at the time to kind of sneak in some survey questions to hundreds and if not thousands of people. And the interesting thing is one of the questions are, how much are you willing to pay for a better experience, either be working from home or gaming? And 80% of the respondents were willing to pay between $5 and $20 a month for something that was not bandwidth related, for a better experience. And obviously, they also wanted the ability to be able to manage it themselves. Now, I'm in control. Right now, I'm gaming. Later on, I'll be working from home or I'll be doing this and that. So providing the ability to the end user to custom tailor their experience. And I'll put the focus on custom tailor here because I'll touch on that a little bit later, was also very key to be able to see the value into if I'm going to pay for $10, I just don't want to assume that everything's taken care of. I want to be able to to configure that, if you will. I want to be able to make my network response to my needs, and I want to be able to measure it as well. So that was very interesting. Now, I know it's self-serving. People will say, "Oh no, Gino, it's your own survey, it's your own data." The funny thing is Omdia came out a year and a half later, and they did pretty much a very similar survey, but with 13,000 people around the world. Their results were nearly identical. I think they came up with 78% of the respondents are willing and looking to pay for a different type of broadband experience. So, well, what does it take if the consumers are willing to pay for it and looking for it? Why is it that that's not being done? Well, let me touch base on the first real case I want to talk about is we got approached by a fiber operator here in North America, and they were really tired because they thought they had one of the best fiber networks in the world, yet they were never rated the best gaming CSP or ISP in country, and that was really annoying them. So they reached out to Nokia, and it finally made its way through to my team. And we decided to do a touch to photon analysis in many parts of the country, and testing their networks against their competition. And what was very interesting is while their fiber network was really good, on average maybe up to 16% lower latency than their competitors. And I'll be honest, their competitors in most markets were the cable operators, the MSOs. So if their latency was lower, why were they never rated the best gaming provider by the consumers? Well, that's because they didn't have the most consistent latency. While they had the lowest one, they also had the highest variance, the highest number of lag spikes and whatnot. And at the end of the day, that was frustrating people. As Bjorn was talking earlier, we can do amazing things around the world with no latency that is, even up to 150 millisecond. You can still play a first-person shooter game from around the world without much issues. There's a lot of things going on in the netcode that takes care of normalizing things. But if you have lag spikes, that makes things quite a bit different. In fact, our real world testing working with studios like Electronic Arts and Respawn and things like that, and has shown that people that are on a fiber network with low latency but a high degree of variability on their latency are actually at a disadvantage against the people that have higher latency. So that was always interesting. Now, for this particular operator, we partnered with Domos, and we went on that fiber network. We brought in new CPEs, we brought in new technologies. But for me, what was important wasn't the network measurements. For me, what's important is, can the end user see and feel the difference? So for this particular operator, we went to find real gamers, people that make a living, Twitch streaming, YouTube streaming, and things like that, pro players. And for over a period of several weeks, as we activated and turned on new capabilities and new functionality, new technology, we did a lot of qualitative survey with them. How do you feel about this? Can you see a difference? Can you feel a difference? And amazingly enough, without touching anything on the fiber network or peering or anything like that, by focusing on providing a more reliable and consistent latency experience, we saw a dramatic improvement in the satisfaction of the end users. That was really the most important thing for me, because I can tell you that I've lowered latency by 20%, but how does that translate to somebody's happiness with their service? It's a hard sell, and I get that all the time. I have Bell Labs people that'll come in, hey, we've improved this latency algorithm by 20%. I said, awesome. How's that going to help my kill death ratio? And I get the blinking eyes, and I say, okay, how's it going to help my FPS? And again, so it's important for all of us in the industry to realize that unless we can translate all of these amazing technical achievements and algorithms, if we can't translate that into something that the end users can feel and understand, then it doesn't really matter. They're not going to be willing to pay for it if they can't understand and feel it. Now, I was very excited at the start of the year because at CES in January, NVIDIA announced that on their top tier premium cloud gaming service, they now support L4S, and we worked really hard with them, supporting them in doing that. But again, how does that translate into real world results? So we took here in Canada, where I'm based, we took a residential fiber connection, and we did a lot of GeForce Cloud gaming. And what we found is, we could do cloud gaming with an average, round trip latency of 62 milliseconds, which is amazing. It was really good. But the default configuration of the CPs, the default Wi-Fi configurations, and things that are done typically to satisfy, speed tests and throughput, can have a pretty drastic effect on the stability. So while the latency was low, the variability was quite high, as you can tell. So when we enabled things like advanced queuing and L4S and things like that, and did the same tests, the same household, the same everything back to back, yeah, okay, our average latency went down, which is even better, but that's not the most important thing. The most important thing was that we were able to dramatically reduce the variability. Now you can see little spikes here, which is on that particular CPE, was just the Discovery neighbor scanning happening on schedule. But we were able to dramatically reduce those lag spikes, which is, again, what the end user cares about if you're doing gaming and video conferencing and things like that. So super excited when we see, corporations like NVIDIA and Apple. I know Stuart will be talking later in the webinar, what they've done to enable better tools to their frameworks, their ecosystems, and their developers to take advantage of this is, I think, is super exciting to us. Now, demographics and spending habits. I call this the Fortnite generation. I really talk about my daughter, my own kids, as an example here. My daughter started university. Her and her friends, they came to me and they said, "Oh, Taylor's dad, you work with computers." I said, "Yeah," you nod and smile. That's all what we do here. We work with computers. And they're like, "Okay, so who do we get for our internet access?" Because they were going to get an apartment. And I'm like, "Oh, that's a great question. Do you want TV services? Do you want this? Do you want that? Do you want fiber? Do you want cable?" And they just looked at me with blinking eyes again. And they're like, "We don't know what you're talking about." I said, "Okay, great. Do you want 100 meg, 500 meg, 1 gig service?" And again, they looked at us, "We don't understand what you're talking about." I'm like, "Okay, well, why is it you care about?" The number one thing is, well, how good is the Wi-Fi? Because we all connect over Wi-Fi. And it dawned on me that my daughter's generation has never plugged in a cable in their life, ever. They've only lived in a broadband, relative broadband, as broadband definition has changed over the years, but they've only known this. They didn't go through the pains that we did, through the dial-up days and the early days of broadband and all of these things. They never went through that. So their thinking about what they want from a broadband experience is radically different. They want something they can customize. And that's why I call it the Fortnite duration. Fortnite is a game that makes hundreds of millions of dollars a quarter as a free-to-play game, because they allow the end users to customize the gameplay experience, skins and events and all of these things, and creating this. I would argue that we need to do the same thing with our broadband experience. Allow the end user to create, to change it to what it is that they care about. And I got this question from a tier one carrier in the US, and they said, "All right, Gino, if you guys are so smart, what would a new carrier do?" I said, "Well, offer them a tailored broadband service." Now, you see all the things on the left, that I've got there that you can think about, but there's also all the things on the right. When you have a gigabit network, 10 gigabit network, 25 gig, there's so many other things that you can do from an enterprise services in the regional context. Now, when I give this, I often get pushback, which is normal. They say, "No, we already offer all of these things." I said, "Yeah, but you don't sell it that way. You don't market it that way. You're still selling me a bandwidth package first and foremost. I don't care about that." Or that generation does not care about that. That's not how they work. They work as buying an app, buying a subscription. That's how they operate, and that's what they want to see from their broadband operator. So I would typically argue that this is really what we're driving to is changing the broadband experience into something they can see, feel, and customize, and really, the willingness to pay goes up significantly once you have the ability to deliver on these things. So I think I'll stop here for a second and see if there's any questions from the attendees here, or maybe even from the other panelists, if there's any questions or comments. So.
I think there was a question in the chat.
Okay.
Dean is asking, is one advantage of a smarter gateway CPE because it is south of the demarcation point for access net neutrality rules?
I love the net neutrality rules because that comes up a lot. Um, the fun thing is that the moment that you provide the end user with the ability to customize their latency experience, you pretty much eliminate any net neutrality issues because it's the operators providing the tools to the end user. It's not creating a fast lane and all of these things. The end user is in control. And yeah, putting that compute capability, opening up the CP into an edge computing device is really a key enabler, and putting inside the home as well, because access networks, either it be DOCSIS or fiber, are getting incredibly good at providing reliable and fast access. But inside the home has always been a lot of the issues. So providing visibility and control through a much more powerful device, it shouldn't be looked at a sunken cost. It should be looked as an ARPU generator. For every dollar more that I'll invest in that CPE, I can extract another $20 at the end of 5 years. So, I mean, that's math that adds up real quick. And, not enough time in this webinar to touch on all the, dozens of different use cases on how you can monetize that edge computing device. But focusing on the broadband experience, latency in particular, is a low-hanging fruit, and it's a no-brainer.
All right, thank
Yeah,
you.
so there was one more question there I really like. What kind of customization are offered at the edge? Well, this is the beauty of the open market. Nokia, as well as a lot of the other equipment manufacturers. It's a playground. There's so much things. Like I'll give you a personal example. For me, when I look at gaming, and what I research and do on gaming for gaming optimization is I actually look at how the games operate. Now, how many of you have seen a queuing algorithm that understands the tick rate of an Apex server or a Call of Duty server? So I know that Call of Duty server is running on 120 ticks. So I know there's 120 packets per second I need to do. I can actually pretty much try and guarantee that in the queuing. So making the devices much more aware and intelligent about how the the applications and services operate does open many doors into how you can customize this. So I think this is it's actually part of the fun is we can go way beyond just saying, we're going to guarantee 2 megs. Well, maybe you do, maybe you don't. But if you understand the characteristics of in details of the application services you're trying to better, I think it opens a whole new world of optimizations as well.
All right. Thank you very much. There's a bunch more questions, so if you do have time, you can answer those
Absolutely.
in the chat. Right. Thank you very much, Gino. Our next speaker is Jason Livingood from Comcast, where he's the Vice President of Technology Policy and Standards, and he'll be talking about Comcast's dual queue low latency deployment experiences. So, Jason, please.
Great. Thanks you. Thank you very much. I assume you can hear me okay.
I can, yes.
Perfect. So let me share my presentation here. Oh boy, now it's asking me to give permission. Hopefully it's okay. Let's see. Do you see my presentation yet?
I see your browser.
Browser. Okay, that's not what we want. Hold on 1 second, please. Sorry. Try again. There. All right. That looks like it should be correct now, right?
Yes, that looks correct.
Okay, perfect. Thanks, everybody. Pleasure to be here today. Sorry for the little snafu there. Um, so I'm going to update folks on Comcast's dual queue low latency deployment experiences. For those of you that have been tracking L4S and NQB for some time, you know that we've been in field trials and we've recently gone into production. So I'm going to give some updates to that. We're obviously appreciative of our partners. We'll have some public, comments in terms of PR comms things in the new year to thank some of them specifically and talk about some of the applications. But in particular, I wanted to thank the core team. Folks often think, especially when you're a big company, oh, you must have this huge team of folks that are working on things like low latency. And while we do have lots of dependencies, lots of teams are off working on their individual implementations, like getting it working in our CMTS or our CPE or fixing backbone and peering edge marking, etc. Really, it falls to a core, very small core of folks that are mentioned here. So appreciate all of their help. So our deployment has officially begun, which is exciting news for us. And just to show, how long some of this takes, we began trials more than a year ago. In April of this year, we reached a tech ready milestone, which from our standpoint means it's ready for production, it's stable. And then you begin, the detailed deployment planning around, sort of when will you do it? What are the dependencies, et cetera. We did find as we ramped to prep for production late in the summer that we had a lot of configuration to do in our cable modem boot files. And it was interesting because the difference between turning on active queue management and dual queue networking was quite different. With AQM, it was really just an on or off, binary choice. There wasn't a lot of configurability that we had to worry about. But we did find quite a bit of configuration that we had to do to sort of get this working for production. And I expect that we will probably learn some from wider deployment and do further iteration of the boot file configurations as we go into next year, which is pretty normal. We're always in boot files, tweaking config parameters. So October 15th, we began our first phase. So we sort of go from crawl, walk, run. So think of it as a very gradual phased deployment. You go into this first phase. We turned up about 20,000 homes in production, and we let that soak for a period of weeks while we look at statistics and any of the other metrics that we track. And I'll talk about that in a later slide. And then this month, we started going into the walk phase. We are almost completely through the walk phase deployment. In fact, our last step of that is late this evening, early tomorrow morning, in the maintenance window when we'll get up to about 200,000 homes live in production. And then in January, after the holiday moratoriums conclude, we'll get into the run phase, which is more than 600,000 homes, or roughly 600,000 homes per week, ending with a little over 4 million homes in that first phase of deployment. As of right now, the CPE that we've used, the cable modems, are the ones that we run and control. So the XB6, XB7, and XB8. Part of the reason for that is that we control the RDKB software that's on those gateways. So it's been very easy for us to update the software in the CPE and iterate that code as needed. We will expand that to customer owned and managed or COAM devices, otherwise known as retail cable modems, in the first quarter. It is likely that the ones that we will focus on are the ones that are qualified for our full duplex DOCSIS or FDX areas. Really kind of two reasons for that. One, they're the most modern, chipsets and Wi-Fi if they have a gateway built in. But more importantly, those vendors are actively in our labs right now, iterating their releases to get ready for full duplex DOCSIS. And so it's an opportune time for them to, be updating code to add the latency DOCSIS support. So we'll look for that. Right now in phase one, in terms of the deployment areas, it's what we call our enhanced areas. So these are the areas that are on a virtual CMTS and have been upgraded to multi-hundred megabit per second upstream bandwidth. The next phase beyond that is the full duplex DOCSIS areas, which are really just rolling into production as well now, where you're getting, 1 gig symmetric or greater in the access network. And one of the reasons that we focused on the vCMTS platform is, once again, similar to our home gateways and cable modems. We control the software in the virtual CMTS, and so it's been very easy for us to do code deployment there as opposed to our legacy integrated CMTSs. So lots to come there, and lots of room to grow. Our entire network, I should say, is also moving to the virtual CMTS platform, and of course moving to the enhanced speed. So eventually, the entire network, will be capable. So moving on. There we go. Scaling up. So I mentioned the different phases that we use. This is very typical, I think, of any production deployment. You deploy in a small number of devices. You have a soak, observe, analyze, decide, or OODA process where you're looking at the effects, and then, based on agreed stability from a variety of partners and parties internally, then you widen that deployment. And so in our parlance, sometimes we start with a very small blast radius, and we expand that potential blast radius so that if something goes wrong, you're not affecting the whole network right away. So that's been good. And we have a really, really wide range of statistics that we monitor, from the sort of link and physical layer all the way up to vCMTS stats, modem health stats, active measurements that run on those gateways, on the XB gateways, passive measurement that is on our virtual services gateway. And so I'll talk about each one of these briefly. Remote PHY stats, so think of this as the spectrum layer of the network, and the physical layer where the coaxial cable connects to our fiber nodes. So looking at any stats there, looking at statistics on our virtual CMTS platform, and modem health stats. So looking at that group altogether, you wouldn't really expect to see anything. But again, with any of these things, because it's tied to a code release, both in the CPE and the CMTS, it's not the only thing that's in that release, right? And so there could be other things, and you're looking for any, pattern variances there, anything that doesn't fit prior behavior. And then we have active measurement on the gateway. So think of idle latency tests, working latency tests, bandwidth tests, etc., aka speed tests, which I know Stuart doesn't like that term, but I'll use it anyway because it's typical. And then we have our virtual services gateway. So think of that as basically a gateway that can observe things like round trip times for packet flows in the network. So a passive measurement where we're just observing and inferring QoE. And then we also look at, very importantly, customer contacts. So we will specifically look at the devices that have been provisioned to see if those people called in, the CMTSs where we've deployed to see if there were any changes, divergences in customer contacts there, including mentions in chats or voice calls of topics like delay or latency or buffering and those kind of things. And then, of course, IP layer and application layer stats. So these might be, other, TCP or UDP stats, or other applications, things that we track for our in-house applications. And of course, partner QoE stats. So because all of these sessions are encrypted, we ask the partners to share client QoE stats, and those have been very valuable. And in fact, early on, some of those partner stats, in particular, some from the Apple team, highlighted some issues with our cable modem boot files, which I mentioned earlier, where we did some iteration. So, that's been a great feedback loop. Our high level observations, the technology is ready to scale. We've seen also the deployment of downstream AQM. So back in the beginning of the pandemic in 2020, we deployed upstream AQM for DOCSIS 3.1 devices. But we never turned on downstream AQM because that was really in the CMTS and it was tied to different CMTS releases and so on. So we deployed downstream AQM at the same time, saw wonderful reduction in the P99 latency under load, which is great. And I'll talk about a very interesting effect next. But we're seeing L4S and NQB performing exactly as expected, and app developers are reporting extremely positive QoE improvements, which is great. Now, the funny thing is, we look for any pattern changes, and this is one that I found hilarious, frustrating for a few days because everybody ran around in a bit of a panic. So we have active measurement tests that are embedded in our XB gateways, and those run speed tests. And so this is an aggregate of many, many users running speed tests when downstream AQM got turned on. So this was not dual Q low latency, just AQM turning on downstream AQM. And suddenly we saw on the left-hand side, you see downstream percent of advertised, which is what POA is. And then the blue line are downstream retransmits. So we always aim to be above 100% of advertised speeds, but we started seeing a little bit more variability in those speeds at the very moment that downstream AQM is turned on. However, at the exact same time, retransmits basically went to zero, which was a great outcome. And the funny part was having an internal conversation with folks that weren't super familiar with what we're doing, saying, wait, our normal level of retransmits went away and now we're seeing like none. And is that good or bad? And that prompted a lot of laughter internally as we dug in and explained this stuff. But what we found was we very quickly looked at all of the third-party speed tests, which showed no change whatsoever. And so it was very clear this was an issue with our own test. And really all we had to do was add a few seconds of duration to the test, and the POA returned to normal in terms of less variation. And of course, our retransmits low, which was a great outcome. But it's another one of those that we're looking for any variation, and sometimes we find that it's not really a real problem. It's just a problem with an active measurement tool, which is one of the reasons why I always prefer passive measurement or observation. So anyway, that was a fun one. In terms of next steps, as I mentioned, as soon as the holiday moratoriums pass, we will significantly widen the scope of deployment, and we will add more CPE models, those OEM devices. And then we'll continue to help other ISPs and developers figure out how they can deploy. And I expect a lot of my time next year will be spent documenting success stories, in part to really help attract more developer interest, and get more engagement. So with that, I will stop, and those are all my slides for today. Happy to take any questions if there are any.
Excellent. Thank you, Jason.
Yep.
There's a question in the chat. So Damien is asking, given all the statistics you analyze, have you noticed any variables influenced by the resilience of the transmission metro networks? This could include factors like longer geographical routes or differences between path A and B.
Well, it's certainly true that distance matters, and we can't overcome speed of light issues. So the shorter that we can make those rings, the better. And so starting, probably this time last year, I started talking to our folks that do physical layer fiber runs in the metro areas and was saying, when you have a choice between a route that is 1 millisecond faster when you're doing something in our regional networks or not, please, preference the ones that are a little bit shorter. But honestly, in this area, I think it has very little effect. We certainly see some network areas where, maybe you're not in a major metro where CDNs are located. And we're working a little bit on that to try to bring those CDNs into the edge network. But it's really a story, I think, between idle latency and working latency, and a few milliseconds of idle latency, while it's important, pales in comparison to the potentially dozens or hundreds of working latency milliseconds. And so, it's this sort of software buffering behavior that makes a bigger difference.
All right, thank you very much. I think there are some more questions about the retransmit metrics and stuff as well, but really need to move to the next
Yep, of
speaker.
course. Thank you.
And Craig, I think you're a bit early because there's Magnus now. Sorry
Okay.
about that. Yeah, our next speaker is Magnus Olden. He's the co-founder and CTO of Domos, and we'll be talking about how we can go from complex network measurements to application outcomes. So Magnus, please take it away.
Thank you. You can hear me, right?
I can hear you,
Perfect.
and the screen is, yes, showing your presentation now.
Perfect. It's a great layoff from Jason. The fact that even people in Comcast are not sure whether high or low retransmit is good. So what does then end user think about what high or low retransmit is? And that's kind of what I'm going to talk about is how can we go from this complex latency statistics, complex network quality measurements that kind of the panelist here knows a lot about, but most people do not understand at all. Really, what they do understand is how well they think their application is performing. So I'll talk about the complexity of that, and then I'll talk about quality of outcome, which is an ITF-ID that myself and Björn has been working on with support from quite a few companies and people. But kind of just to set the stage, I think it's really fundamental that users consume applications and not networks, and certainly not latency. If you look at kind of the share of the population that understands latency to any extent, then the impact it has on their application performance, it is certainly very low. Right? So we need to talk about applications performance rather than these network statistic. If the dreams that kind of Gino talked about, the more service-driven broadband offering, if that's going to come to fruition, we need to start speaking a language that the consumer understands. And that is the language of applications and not of networks. So what will I talk about? So first I will start setting the scene, like what is so difficult about network quality and application performance? Why is it difficult at all? When I talk to people I studied with, and we did information science and statistics and AI, they do not understand why it is difficult from a network to understand the application performance. And these are relatively well-educated tech people. They do not understand it. So I'm going to go a bit into that, talk about the measurements, talk about why it's so hard to aggregate, why applications are hard to measure, and how they kind of interact with the network and how user experiences. Then I will talk about quality of outcome, which is this network quality framework that we propose in the ITF to get around a lot of these problems, and the design goals to make it kind of a middle ground between latency measurements, bandwidth measurements, and whatnot, and these quality of experience measurements. And how to make it useful for end users, for network operators and vendors, and applications. And then I will talk a bit about some results we had from a user trial we did with Comcast, thanks to Jason Livingood, who was the previous speaker. And we have some great results about how end users actually perceive quality of outcome. Okay. So what's so difficult about going from latency measurements to application outcomes? Well, first we talk about how to measure the network quality, right? So speed test bandwidth is what we learn to know. It's what is being sold. If you follow this webinar, if you follow what Windows have been talking about for years, you know that latency is very important for the application performance. But latency also comes in many forms. You have idle latency, you have latency under load or working latency, which many others here are working on. Then you have this kind of looking at the peaks, looking at the median, the 50th percentile latency, 90th, 99th, etc. And then you have packet loss and retransmissions. Like all of these are dimension of network quality. This is just the first layer of complexity, right? You have different ways of measuring it, whether it's speed test, whether it's with something like ping, or TVAMP, or SOMP, or real-time response under load. There are lots of complexities here, right? Both for this active probing, and you can do passive measurements, like Jason also talked about, by monitoring traffic. But there's just a lot of complexity here. And when you do this measurement, if you do it continuously, just one time, this really matters. But the fundamental difficulty here is that network quality, it changes very frequently, many times per second, and also radically, right? The example I always use is I can take my phone, flip it over, and due to the extreme amount of signal processing that is being done, that flip of the phone can actually reduce my effective bandwidth to nearly a tenth, just because of how like MIMO signals are hitting and whatnot. So it's a radical difference for my flip of a phone. And that means that aggregating network quality measurements is really complex as well. One thing that I know they will talk about is that time is complex, right? So, you know, we can have thousands of packets per second, and if the network quality can change radically within that second, how do you measure that? Like we're used to talk about megabits per second. I know people have proposed that bits per millisecond is actually a much better way of looking at it. And of course, when you aggregate this over time, if you look at the average speed over an hour, everything looks very different. The statistics of it is also different because applications are very much affected by the peaks, right? The high percentile stuff, like the absolute peaks, makes a huge impact on some applications, more so than the average. So how do you make sure you capture these peaks? How do you make sure you capture the kind of type of variation that there is without having to know the latency of every single packet? Because if we need to know the latency of every single packet, we would create so much data that would be impossible for us to use. So we need to use statistics to do this. And then you have another problem, which is, do you look at this only end-to-end, or do you look at network quality per segment as well? It is really difficult because perspective matters. Like we work on putting software on CPEs and are looking at, hey, the Wi-Fi network, the access network, the core network separately. If you go to someone like Ookla or someone who does a speed test, they look at things end-to-end. If they look at an app developer, they look at things end-to-end. But we need to work together. If the network vendors, the network operators want to improve the network quality for the applications, they need to understand how each segment are causing variation, right? And this just makes everything more complex because, well, networks are complex. You're looking at Wi-Fi technology, a DOCSIS, a fiber, all of these aggregates to the end-to-end perspective. And just to make things even more difficult is that not all technologies measure this the same way, and not all operators test and measure latency and bandwidth the same way as well. So lots of complexity in the aggregation as well. And of course, applications have spent the last, well, since the beginning of the internet almost, trying to figure out how can they counteract poor network quality. How can they adjust their resolution? How can they use different codecs? How can they adjust the packets per second? How can they adjust their jitter buffer or bitrate adaptation to create as good as possible application performance, even on a poorly performing network? So if you want to look at the network quality or the app performance from a network perspective, you have to take all of these things into account. And this makes it very difficult, especially since you have multiple layers of optimization, right? I talked about the app layer adjustments here, but you're also the network protocol layer adjustments as well, like with TPC, TCP, what it does, and UDP, and it's built into WebRTC and whatnot. And you have these different application types doing things differently and reacting very differently to different network quality. And user experience is just even more difficult because two people experience the same video conferencing differently. Your mood may affect your experience, your expectation may affect your experience. So it's just not measurable in a scalable way. So while user experience is not measurable at scale, application outcomes are, or at least close to it. And that will strongly correlate to user experience, which is why we made quality of outcome. We propose this as a standard in the ITF. Okay. So quality of outcome is a proposed middle ground between quality of experience measures and quality of service measures. While quality experience is relatable, like you can ask someone, how do you think this performs? It is unreliable. You can't optimize a network like that. While quality of service metrics like bandwidth, jitter, packet loss, latency under load is certainly reliable, it's not relatable. Like people don't understand. But what is the likelihood that you will have a perfect video conference? Is kind of the middle ground we found that's the best because it's relatable, at least to some extent, and reliable. And we also wanted to make sure it was useful for application vendors, for end users and operators. So we had some goals to make it short. For the end user, it needs to be understandable. It needs to have something to do with the application outcome. And of course, it has to be honest and objective because they need to trust it. For the application, this trust, the honesty and objectivity is also very important. But it needs to be able to understand how the application will perform, and whether it will perform as intended, and to be able to describe very complex network requirements and very simple network requirements, and on very complex network conditions. And we also think it makes a lot of sense that it's probabilistic, because with just a flip of a phone, you can change the network quality a lot. That means that for an app, it will always be probabilistic. The app do not know when the user will flip their phone. And for the network operators and vendors, this objectivity is of course important, but having a strong mathematical foundation is also very important. Why is that? Well, from inside the network, you won't be able to understand which network segment, which network router is actually contributing to the reduced application performance. And to do this, you need composability. You need to be able to add the different segments up and subtract them from each other. And it needs to be useful throughout the cycle. Like you need to be able to do lab testing, active testing, monitoring for it to be useful. If all of this is possible, then the network operators and vendors can ensure they are improving application performance. So proposed solution is quality of outcome. It's an ITF ID. So here's the link. I think you should check it out. Basically how it's built to work with aggregation and measurement complexity, we built on top of TR452, which is a broadband form standard, which fixes a lot of these problems. But how do you aggregate network quality? How do you measure it? How do you compose it? How do you capture all the dimensions? And that was already done, so we could build on top of it. And we needed to allow these complex app requirements, but also take it back to probability, so it's understandable. And the formula can be visualized like this. And I won't go through it because I do not have time, but it's basically setting up network requirements as, or you can set up very complex network requirements and calculate the probability that you are meeting them. And then I want to talk about a user trial we just did with Comcast Innovation Fund, because that goes into, does this resonate with people? Do people like quality of outcome? So we had Comcast Innovation Fund user trial. So since it was Comcast Innovation Fund, the results are open. 25 routers were sent to Comcast customers. We tried to make it a representative population. And we wanted to give the end user a tool where they can look at their quality of outcome per application type. And that also helps them improve the network quality by putting network quality into quality of outcomes. And then we gave people a questionnaire, like, how do you like this? And people really, really liked it. So 86% says quality of outcome more accurately reflects their experience than their bandwidth. Every single participant said that this was better than the speed test and latency and jitter. And people also like that quality of outcome is based on an independent standard, and they would highly recommend it to a friend or a colleague. And I'll just leave you with this one last thing, which I think is very interesting and kind of surprised me. So 53% of the participants said they would rather buy application guarantees than bandwidth. Like, think about how drastic change that is for this industry. Like, it's not 100%, but it's still 53%, which was much higher than I expected. And 80% say they would rather buy from an ISP, which had app performance guarantees in addition to bandwidth guarantees, which is kind of shocking numbers, but it also reflects kind of what Gino has been saying in the first talk, is that people care about the application performance. We are beyond speed. We just want it to work. The app performance is what's really important. So thank you for listening. If you want to get in touch and contribute to the quality outcome framework, let us know. We are very happy to do so.
All right. Thank you, Magnus. I think there are a few questions both in the chat and the Q&A. So first, Ian Wheelock is asking, how can customers that volunteered for a trial be representative of a population of users?
No, so I'm not saying they are, but I say we try to make it as representative as possible. So what we did is that we offered a $200 gift card for all participants. And the reason for this is just what you say, like that if you just ask for the volunteer, you will have a very geeky crowd. But adding the incentive just kind of changes that population up a bit. So I'm not saying this is perfect, but we tried, and for the scale that we did the user trial on, it's I think the best we can get to.
All right, thank you. I believe there are a couple more questions as well. I'll put up the break slides now, though, because we planned for a break because we know the importance of having some flexibility in timing. So there will be now a short break for 10 minutes or thereabouts until 17:20 Central European time, and then we will continue with the next speaker. If you do want to answer the questions live, though, Magnus, you feel free to do that. All right, we're coming up on the end of the break. Craig, if you're here, you can share your screen and get ready. But I'll wait. Well, we can wait a couple more minutes just so that everyone is actually back from the break before you start here.
And in the meantime, you can see it okay.
Yes, it looks good.
Thank you.
And I can hear you very well as well.
Thank you.
All right, I'm going to assume most people are back from the break now. So please welcome our next speaker, Craig Thomas from the Broadband Forum, where he's the CEO. He'll be presenting about quality of experience and the transition to services-led broadband. So please, Craig, take it away.
Thank you, Bjorn, and thanks for everyone else before me. They were the intelligence. I'm the follow-up act after all those intelligent conversations. So in this next 15 minutes, I'm just going to share what I call the jigsaw pieces when it comes to latency and QoE inside the broadband network that the BBF itself are focusing on, and our transition really towards what we're calling a services-led broadband. So from a BBF, just at a very high level, we are refocusing on where we're going. For the past 30 years, can you believe that? 30 years, we've been focusing predominantly on solving the connectivity problem. You know, how do we, from the data center all the way to the customer premise, deliver the broadband speed, capacity, and reliable connection? But there's a slight transition. We don't lose that focus. We continue to have, solving the problems of connectivity, and now moving from PON technologies of 25 and 50 gig, and even now coherent and 100 gig when we're looking at that speed and that connectivity. But increased focus on what we're calling this services-led broadband. And that is really what, when it comes to latency and QoE, is critical of driving more intelligence inside the broadband network with service level as well as application appropriate understanding and QoE demands as part of that, so that we're going beyond just that speed and capacity and enabling the broadband to meet the applications that subscribers want from their services, and give those broadband service providers the chance to differentiate, add value, and monetize, as Dion was mentioning earlier. So every 2 years, we do work very closely with Omdia, and we build a survey. We interview well over 100 global service providers and interview them, as well as come up with some real great conclusions. And one of the questions that we had nearly a year ago when we published this survey, and we're going to be doing it again this year, in 2025. But one of the questions we had was, what are those service providers' plans in regards to differentiating customer QoE on a per service level? And this shocked me that over 72% are already planning to differentiate on a QoE and latency per service basis. So what does this mean? Well, we've got to add that application aware intelligence, and the monitoring of it is going to be critical to making that relevant. The QoE per application will be a key differentiator. When we're looking at the network today, and the only differentiator really is speed and price, and now moving up the value chain so that they can do relevant QoE per application is going to be critical. But at the end of the day as well, we have an education that needs to happen at the end user level. when you look at, we always go to the gaming example or the working from home example for QoE. Well, depending on which country you are, gaming households represent around about 20% of all households. Working from home is actually decreasing slightly since the massive uptake during the COVID time. But that's still only around about 25% of roughly on average for Western economies that are requiring a work from home service. What we've got to do is educate, and Magnus was talking about this, in relevant terms so the end user understands what QoE means, what latency means. And it has to be from an end-to-end perspective. Interestingly, we did our own survey going around all the forums and asking and looking at those markets that are offering multi-gigabit broadband connectivity. And when you look at the forum and the influences that they have on those forums, commonality is that more than a gigabit speed is not necessary. You're getting a lot of people out there that are active gamers, that are working from home, that are hyperscalers, who are basically saying to their representative communities, you don't need more than a gig. So QoE and the latency that we can educate those people with will be the differentiator moving forward, more than trying to sell 10 gig to a service as a service to an end user. In that same survey, we asked them, well, what are these new value-added services that you're going to be asking for? And pretty much you can break these services down into two main categories. One, which is the early take-up, is just, I've termed connectivity plus services, which is just basically adding to the connection with speed test, with managed Wi-Fi, with in-home connectivity and voice assistance, and cybersecurity and security on top. But then you're now looking at the next generation of services. Now, you may want to call this a move from telco to techno provider. But when you look at this, and I know it's a bit of an eye test of a slide, but you look at all of these secondary services, which are still having around about 50% of service providers wanting to start adopting and offering these services, then latency and QoE suddenly become really important. The streaming video services, the gaming services, the e-health services, even the managed IoT services, where there's going to be some element of QoE is going to be critical to be offering those services themselves. So from a broadband forum point of view, what are the pieces of the jigsaw that we think is relevant to offering the end-to-end network? We can talk about individual parts of the network and AQMs and areas of metro edge compute services, etc. But when you want to offer QoE, it has to be end-to-end. And I'm talking about wherever you're hosting, whether it's in a data center or a metro edge, all the way to not just CPE, but to the device and the application inside the device. And that's where the measurement has to happen. So from a BBF point of view, do we have the whole jigsaw? No, we do not. But these are the elements that I see from a broadband forum, and our membership is working that is very relevant to latency and QoE. First of all, there's the work here in the connected home, where we're doing things such as the work on containerization and smart gateways, that you can just drop in a container, a Docker, that's appropriate to the measurement tools that you want to use, whether it's Wi-Fi QoE mechanisms, whether it's added on cybersecurity, or the actual applications themselves. And then we also have within that home the user services platform, our TR369, as well as our Wi-Fi performance management inside that. So really going from the home out towards the data center, the next level of work that we're doing is on UDP-based speed tests, so that having accurate speed tests, well in excess of where TCP sort of lags out at 700 or 800 megabits, the ability to use UDP for your speed test to multi-gigabit. But in addition to that, on those speed tests, not just having a ping test, but a continuous latency management testing, so that you can actually have recorded network performance on a latency basis across the speed test itself built in. And that work is being required and built by the service provider community itself. So, organizations like AT&T are building that mechanisms, the software, the tools to make that happen. After that, there's the quality attenuation, and I'll touch on it, but thankfully Magnus also talked about it as well, our QED quality attenuation, and there'll be slides on that. And then looking at something that is really bringing in the intelligence in the edge core and the middle mile, as well as in the access network, where we're starting to look at the ability to do agile session steering that will work hand in hand with that quality attenuation. Some new work that just got started in the last 6 months on L4S and what that means for the fixed broadband network itself. And then trying to put all the pieces together in an SDN NFV world of how do we look at automated intelligent management to drive the agility from all of those mechanisms to have the network aware on the level of quality that you're expecting to see in the network, and understanding of where there are events in the network that you need to fix. And those last 3 or 4 jigsaw pieces, I'll just go into a little bit more detail on. So Magnus touched on this, and maybe I should have touched base on Magnus before putting this slide together, so apologies for that. But we've been working on something called QED, Quality of Experience Delivered, now for a number of years. And some very intelligent engineers, mathematicians have been putting some work together. The likes of Domos have been heavily involved, PNSol, Outsys, but other organizations specific from the service provider community, Vodafone have been very active in this work as well. And we appreciate that broadband is pretty good at the moment, and lots of packets get delivered at the right time quickly. And usually the average of those packet deliveries is pretty damn fine. But there are the rare exceptions that make the difference to that user experience. And what QED looks at is the need to measure the delta away from perfection that is allowable. So we call this quality attenuation. We terminology as a delta Q. And it changes the focus of the network from more of a capacity to what is now less of an attenuation. So QED provides a mathematically robust performance measurement and analysis technique that integrates packet loss and packet delay instead of treating them separately. So we decompose a round trip time in 6 latency metrics. And those delta Qs have a wide variety of applications for broadband service providers, such as using it for root cause analysis, for network operations, access technology performance itself and characterization, and consumer broadband quality KPIs in the home network for optimization as well. And when you add that quality, that QED, those delta Qs into an intelligent network delivery, then we start looking at how we can work closely with the SDN NFV management and network agility that it delivers to the network itself, so that we can now have QED that will automatically set alarms within a network and do clever things such as session steering. So if one path in the network is not performing to a set attenuation requirement, we can now dynamically session steer to another BNG or AGF or CMTS or whatever it may be. And we did this demonstration for the first real time with an automated intelligent management platform back in October of this year at the Network X event in Paris, where really we looked at how can we build all of these pieces together where you're having multiple OLTs, multiple BNGs, probably from multiple different vendors, and then build the QED analyzer inside of this, hand in hand with our automated intelligent management from an SDN point of view, so that we recognize at any one time that one session is not performing as we want via a BNG to a router in the middle mile, and ultimately to wherever that QED reflector would be, and dynamically rearrange that so that we can change that session and steer it to a different DBNG that may be underutilized or just has a better path and performance that time. And that's just one example of where we can start looking at AI, SDN NFV and a cloud CO type environment, and then using things like delta queues and quality attenuation to build this intelligence into a better network performance. No, of course, it also offers some sort of benefits when it comes to sustainability and carbon footprints. But from a QED point of view, this is really just the ability to dynamically session steer according to whatever parameters you set in your network. And then another key area that, as I mentioned, that we just started is working on L4S for broadband. And now L4S is not new. The IETF with their RFC 9330, 331, and 332 have been doing this for a number of years and updating that. And people like Cable Labs have been looking at it from the cable DOCSIS perspective. But this is new work that we're starting inside the Broadband Forum specifically for the elements of a fixed broadband network. So L4S, low latency, low loss, scalable throughput, is allowing supporting hosts to basically fairly share a network capacity without building a queue, therefore delivering good throughput for all flows with consistency and low latency. So what we're doing here from a BBF point of view is looking at, well, where do we want to implement L4S in the fixed broadband network elements first? So we're reviewing L4S and where we want to prioritize first between the RG or the business gateway as well as residential gateway, the access nodes, the Ethernet aggregation, and the service gateway as in a BNG or a BRAS or an AGF, and look at how we deploy that so that we're not adversely impacting existing traffic, but we're identifying and defining any changes required to the broadband forum data models, as well as looking at the end-to-end L4S model inside all of those network elements that you would see in a broadband network. And I think critical, and we're easy to forget about this in latency terms, but this scope has to include wholesale deployment models. So we can stop that finger pointing issue where you are looking at markets, whether it may be in the APAC, Europe, or increasingly in North America as well, where there's an open access or a wholesale broadband model. And then we can look at some kind of QoS, QoE latency models that are applicable to wholesale network provider as well as the retail service provider. And that work needs to commence and continue so that we're meeting the whole remit of where you're seeing broadband networks today, both from a retail point of view as well as a wholesale point of view.
Right. Thank you very much, Craig. We are a tiny bit over time, so I think no problem. I think we will skip the live Q&A for this one. There's at least one question in the chat and one in the Q&A. So if you have time to get to those, that would be very good. Thank you very much. Our next speaker is Benoit Claes from Huawei Ireland Research Center, where he's the Data Communication Intelligent Operations Management CTO. So Benoit, please. Sorry. And the title of his talk is Measuring Network Latency, Latest News from the IETF. So please, Benoit, take it away.
Very good. Thank you. So I'm sharing my screen now. If you don't see it, scream. So thanks for the introduction. So measuring network latency. The first question is why? The question is, the answer is because we want to solve the vision of autonomous driving networks, where we will go from level 0, where we actually use CLI to configure devices, to complete autonomy. And the network latency is one of the key KPIs that you need to look at to have a network that's going to manage itself, right? We have cars that self-drive these days. Why not networks? So that's the vision. Now, let's go one step further.
Benoit, I think maybe you're sharing the wrong screen because I can see your slides, but it's on the first slide at the moment. Oh, there we go. Now it's slide 3.
Right, but I'm not in presentation mode.
Oops, I think we lost Benoit there for a while. He'll probably be back soon. Yes, now I can hear you.
Right, but which slide do you see? I'm going to share.
Now I don't see any slides yet.
Okay, interesting. Let me try again. Okay.
Now I see slide 2 in the PowerPoint view.
All right. Realizing the ADN vision, right?
Yes, that's right.
Very good. So let me just explain why do we need to solve ADN. Because in the end, this is always a network fault, regardless of the problem. Not sure if you noticed that, right? We always say, oh, let's blame the network. Fine. Even if sometimes it's a server issue, right? In operators, that reflects the fact that we have different teams, one for the network, one for the servers. And just proving it's not a network issue is a big deal because it means that we're going to redirect the issue to the server team, right? Sometimes the server is overloaded. And the issue is that the network complexity we've been loving is on the verge of turning against us, right? The network are more and more complex to manage, need automation, we know it, but let's start the basic, network latency. Now, which one? And I would say in a network, we only deal with the issues that are customer impacting. So let's focus on the customer service. I saw in a chat before, like, what is a service? What is an application, right? So for this, I want to introduce a new architecture, which is about service assurance for intent-based networking. In there, we created an assurance graph, right? With the idea that whenever a service instance degrades, we could directly find the fault and the symptoms. And now, whenever we find an issue in the graph with a specific component, we want to understand how many service instances are impacted.
Sorry, Benoit, I think maybe we're on the wrong slide again. I'm still seeing slide 2.
Okay, so Anna, can you please share? I don't know what's happening. I'm moving
I
my
see. I
slides
mean,
here.
I see your slide, but it's in the it's sort of in not in the presenter view or in the.
Okay.
Yeah, we are seeing the presenter view is probably the right thing to say. Now
Okay.
I see slide 4. Yeah, there's your mouse pointer as well.
So please share the slides on your side. I send them to you, Anna. Okay. Whenever you do, let me know. And let me know on which slide you are. I would like to be on slide 4.
Oh,
Yes, I'll share them. Just give me 1 second.
thanks, Nina.
So let me keep talking more. So the idea is that, okay, we want to look at service instance. From there, think about having like the impact per service instance as a symptoms. And then we would know exactly on slide number 4, you would know exactly what the issue is, assuming you've got the customer on the line. So in this presentation, I'm going to send you a couple of pointers like the 2 RFC at the bottom. Good. On the next slide, we know that we need to focus on services. Great. Let's look back at the history. In a previous life, I was dealing with, next slide, please. Yeah, I was looking at IPSLA from Cisco, which is sending active probing from router A to router B, or from router A to a server. Fine. The issue with active probing is that, is this really the customer problem? Is this really the customer service? Is this really the customer traffic or application? Because you're sending from your own source IP address to a specific port at a destination. You are not really mimicking the customer traffic. The next issue is the N-square problem. If you want to have from any provider edge router in a network or any point of presence, each time you add a new point of presence, you need to configure a new probe in both directions. So you got the n-square problem. This implies a heavy operational burden each time there's a change in the network. Now let's discuss the accuracy. If you know about router design, like a ping or a packet whose destination is a router itself will have a lower precedence. It's like process switched to the router itself, which means that the timestamp you're going to receive is not specifically accurate. And you care about the traffic going through the router to destination. So for this, we created Shadow Router, which is like a router dedicated for active probing in each POP. So it solved a couple of issues, right, for the accuracy, for example, because you're going through the router. However, on the next slide, the biggest issue with active probing is that the biggest issue is ECMP, right, equal cost multiple pass. You don't know the pass that was used by active probing. And you don't know which one has been used by the customer traffic. And you've got the customer on the line. So in a data center or in a core full of ECMP, maybe you're looking at the wrong stuff. You will see, oh, my active probing tells me there is no issue, but there is an issue with a specific link, ECMP link. And you can be thinking about it a lot, but without knowing the hash function of the router, which a router vendor will not share, you really never know what you observing. There are some mechanisms where you're going to take all different combinations, but they don't work actually. You're sending too much traffic. On the next slide, let's introduce the IP performance metric working group, full of metric definitions such as the one-way delay, but also packet loss, delay variation, etc. And the two protocols, OWAMP and TWAMP, the one-way and two-way active measurement protocols, they have the same issues as the active probing mechanisms. So what is more interesting is that the last bullet point, what we call hybrid methods, which is a way to combine active and passive attributes. So let's keep in mind for now, I'm going to mention that again. So on next slide, let's introduce one more piece of the puzzle. IPFix, IP Flow Information Export. So we went from Cisco proprietary NetFlow to IPFix, where at any ingress point of a network, you could select to look at the data plane monitoring with looking at all the packets arriving to interface or leaving an interface. And you could classify this based on the typical tuples, IP addresses, ports, QoS, etc. And then you count the number of packets and bytes. Great. Now we could be sampling, not sampling, technology specific, but now that you know this, on the next slide, what is missing compare if I put all these together? So we want to have service, which could be a flow, which could be an application. We know about flows, we know about delay. What has been missing all the way is that we want to actually observe the customer traffic with flows, these specific IP addresses, source, destination, port, etc., and adding the delay on top of that, the delay measured directly in a router. So if you take like from bottom to the top to the bottom, the packets arrive on the ingress interface. And you're going to select a couple of interesting packets, for example, in the top QoS queue. Those packets will be tagged with a timestamp, right? Then those packets will continue through the router at the top to the router at the middle. At the next ingress point, you're going to look at those packets again, the one that were tagged. You will have the time that you observe there, and you will be able to deduce the delay of the router processing time on router 1 and the transmission delay on the link, etc., etc. So what do you have? You have, for this flow going from the top router to the bottom, the flow information. So you have the customer on the line. You could check exactly if we speak about the same flow. Then you have got the delay. And what we export directly next to the flow is the min delay, the max delay, and the sum of all the delays. The sum y to deduce the average. If you can export directly the average. The point is that whenever you have that for all the ingress interfaces of your network, you have a statistical view of all the link delays. And if you want per specific flows, and you would see directly if there is something happening on any link of your network, even ECMP. So we measure this with an internet marking, an RFC there, or what's called iFit in Huawei. On the next slide, does it scale? Well, it does. So IPFix on every interface of every router, and it scales up to, in production, 2.5 million Kafka messages per second. Is this accurate? Yes, of course, you need to have time precision. I was just forwarded this link there with NTP interleave nodes that allows more accurate transmit timestamp. So it scales, it's accurate. On the next slide, I want to stress one thing, the data mesh principle. If you haven't read that book, that should be a good one. You could be looking at IPFix, Yang Push, and BMP and collect all the information within this data mesh architecture. There are a couple of pointers there for your reference. On the next slide. The issue is, and this is almost my last slide, right? The issue is that we always want to have like end-to-end. And for this, I'm betting on segment routing. Why? Because I see a migration to segment routing v6. I see that segment routing v6 goes up to the cloud. With segment routing v6 programming, you could go up to an application inside the cloud. I see that segment routing goes into, start to go in the access, so we'll be to the access. And we've got the IPFix for segment routing v6 and MPLS segment routing. So we start to have a pretty complete picture. And on the last slide to conclude, so I spoke about measuring network latency. I believe in two hybrid methods to be sure to have active and passive with the customer information in the flow. I believe into doing the aggregation where you can directly, so out of the router. And yes, it's scaled. The measurement is at marking. I believe a lot about linking this with the customer traffic, with the customer information. I believe into SRv6 for the end-to-end. And these are all the building blocks we've been working on to solve the autonomous driving networks. And with this, I welcome any questions if there is time.
Thank you very much, Benoit. That's excellent. We have one question in the Q&A tool. Satish is asking, how can we enforce SLA on all routers? If all routers are profiled before deployment, then it may be possible. Your comments, please.
Enforce SLA on all routers? What do you mean? Do you speak about the SLA measurement or enforce SLA on all routers? Do you mean
I am
SLA
not
for all the
sure.
paths? SLA for all the paths?
Satish, maybe you can elaborate on your question in the chat, and then we can take the question there. Thank you. Thank you very much, Benoit. Our next speaker will be Dan Seaman. He's the founder and chief product officer at Aterlo, and he'll be presenting a small study on DSCP usage at US regional providers. So Dan, please share your slides.
Great, thanks. Can you see that properly?
I can, yes.
Excellent. Okay, yeah, so I'm going to talk a little bit about DCP usage at US regional providers. A little bit of history, I guess, here. I've been meaning to do this for a while, both from a product development standpoint and just general interest. And when I saw the call go out for the conference, I thought, well, if I volunteer to do this, I'm going to be forced to actually go collect the data and get this done. So that's basically where this talk came from. So as Bjorn mentioned, my name's Dan, co-founder and CTO or CPO of Aterlo Networks, better known as Perseem. I'm not going to talk too much about this right now. Okay, so what did I want to do? I was looking to understand a bunch of things related to DSCP. And a few of these questions that I wanted to answer are things like how prevalent is DSCP bleaching in our customers' networks? What percentage of traffic is DSCP zero if it's not bleached at all? What is the distribution of traffic by DSCP? What is the distribution of traffic by DSCP in the evening versus the afternoon, peak and off peak, as it says there? What's that distribution look like in the downstream and the upstream? And does it look any different if we look at this versus packets versus bytes? So I set out to collect a bunch of data and try to answer a few of these questions. And basically, we're just going to structure this as trying to answer each one of these questions as we go. So the methodology, so I collected statistics from 6 different ISPs. I used 2 different mechanisms, which I'll get to in a second. I collected in 2 time periods, afternoon and evening, to try to get that non-peak and peak time. I collected downstream and upstream counts and bytes and packet counts. 2 different directions, downstream and upstream, and bytes and packets in all of these cases. Built a little data pipeline for this. That was kind of fun. Ended up being a lot of charts. It's actually more than 56 because there's a bunch of aggregated ones. Not going to look at them all. I turned some of them into animations, as you'll see, but there's quite a bit of data here. I used 2 different mechanisms to collect this data. So the first is I wrote a Rust dbDK program that I could put on mirror reports and count traffic in real time. So I used this at 2 of the 6 ISPs. That was hundreds of millions of packets for each one of those 2 ISPs. So that's a very big sample. The other mechanism is I grabbed 250K packet captures in each direction from the 4 of the 6 ISPs. So smaller sample size. I think you'll see when you look at the distributions and stuff here, it still seems to be pretty representative, but it is a much smaller sample than the first 2, which are based on a very large number of packets. So the first question I want to answer is how prevalent is DSCP bleaching and what percentage of traffic is DSCP zero? So to do this, created a few charts. This chart has the percent of packets in the network that are DSCP zero on the left-hand side. That's the y-axis. And then the x-axis is each of the ISPs, just labeled ISP A through F. So you can see that in the downstream, and this is afternoon, so like non-peak in the downstream direction, traffic heading towards the subscribers. So you can see here that the traffic is about 90-ish%, just kind of eyeballing the charts there, with the exception of the one anomaly, which is ISPB, which you'll see shows up through the rest of the charts as we go through. But very significant portion, like 90% plus is DSCP zero, so very little other marks present in these samples from these ISPs. If we look at the evening, it's kind of hard to tell from here. So this is kind of peak time, but the bars did mostly shift down a little bit. So there's slightly more marked traffic during peak than there is during off peak. And as we go through the rest of these charts, you'll see more and more of that, I guess indicating that the applications that are used during peak tend to mark their traffic more than the ones that don't. And last comparison on DSCP zero directly, if we look at in the upstream direction, you'll notice that this looks very, very different. Virtually all the packets, like high 90s% for all the ISPs, are marked as DSCP zero. So very little variation. I did not bother including the chart here for the afternoon because it looked almost identical to the evening chart. So very, if I just jump back a slide, very different profile in the upstream heading towards the internet than in the downstream. Okay, so questions. So how prevalent is DSCP bleaching? None of these ISPs, none of these 6 anyway, seem to bleach all their traffic. So I don't know if they bleach some, but it's not all. And then what percentage of traffic is DSCP zero? Well, across these ISPs in the downstream afternoon, it's a little more than 90%. In the downstream in the evening, it's a less than 90%. And the upstream in the evening, it's 98%. And again, the afternoon looked almost the same, so I didn't include it. All right. Next question that I wanted to answer is what is the distribution of traffic, does the distribution of traffic by DSCP differ between peak and off peak? So specifically that afternoon samples and then the peak time samples. So to do this, the first version of this I made, I had a whole bunch of charts and was just going to page through them. It didn't work very well. So I decided to try to make an animation out of this. I haven't tried to do this in a presentation before, so I hope it works. You may need to go full screen to be able to see the fonts here. So I'm going to explain this chart a little bit because there's actually 4 dimensions here. So the left-hand side, the y-axis, this is the percent of packets. The x-axis is the DSCP value. It's just prefixed with P because in the data frame that I used, I named the columns that were percentages with a prefix of P. So the first column is DSCP0, last column is DSCP63. The colors are afternoon and evening. So that's those two time periods. And if you're watching it carefully, you'll see that it's actually animated. So it's one frame per ISP as it moves through. So we're trying to show four different things here, four different dimensions. So a few things that we can call out looking at this. ISPB, as we mentioned earlier, is a big outlier in the downstream direction. You'll see when it pops up, it's going to come right there. Its profile looks very different than the other ones. But even outside of that one, there's a pretty significant variation across the ISPs. And if you look at the height of the bars, which is afternoon and evening, you see that in some cases, there's a pretty big difference between afternoon and evening within an individual service provider as well. It's a little bit hard to see. I mean, I hope that you guys can see it zoomed in, but on the bottom there, the non-DSCP bars, they do shift a bit, but again, they're pretty relatively small amount of traffic. I think if I had to do this again, I'd probably make this a log scale. It was suggested to me, but I ran out of time to do that. This is the same chart in the upstream direction. So as we saw earlier, this is heavily biased, or most of the traffic is DSCP0, but there is one ISP, and that is, I think, E or C there, that there shows a pretty significant difference between afternoon and evening. Don't exactly know what causes that, but you can see that one DSCP P8 there, the DSCP 8 gets a lot more traffic for the afternoon. And the non-DSCP 0 traffic really does vary across providers. That's something we'll circle back to at the end, which I think is surprising, just given the nature of these specific ISPs. Okay, so the questions. Does the distribution of traffic by DSCP differ between peak and off-peak? Yeah, it does. There's a significant variation in the downstream. There's a little bit of variation, but not as much in the upstream. And there's a lot of variation in the service providers. All right, next question I wanted to answer. Does the distribution of traffic by DSCP differ between downstream and upstream? So this is kind of a pivot on the same data where we're now going to have the colors be downstream and upstream instead of the time periods. And I'll just let it sit here for a second so everyone can hopefully take in the animation. Again, we see the upstream is consistently more DSCP 0, and the downstream DSCP usage varies a lot across providers. So again, in this case, the blue color is downstream, the orange color is upstream, and it's animating the 6 different service providers. So really, I think the interesting bits here is obviously the differences in the bar heights, but really what's happening across that x-axis when we see different marks used in different service providers. And again, most of this data was all collected quite close together in terms of time. And this is the same thing, but looking, this one's the evening, sorry. The first one was the afternoon. That's the slide we just looked at here. This one is the evening. I didn't put any notes on the slide because it really looks almost the same as the afternoon. A little bit of shift in the downstream, again, as we mentioned earlier, where there's a little bit less DSCP 0, but it really substantially looks the same. So does the distribution of traffic by DSCP differ between downstream and upstream? Upstream is more consistently DSCP 0, and there is a lot of difference between these ISPs and what's marked in the downstream, what marks are used in the downstream versus the upstream. All right, last question I had time to investigate. Is the DSCP distribution different when looking at bytes versus packets? So in all these cases, basically had counters for each DSCP value, and then had a separate counter for bytes and packets, incremented them as appropriate for each packet. So does it actually matter when you're looking at DSCP usage, whether you count bytes or packets? This slide is a little bit different than the other one, but it looks mostly the same. This is one ISP in the downstream direction. I believe probably the evening. I forget exactly what I did there. Oh, no, sorry. This is the one that has both. It has afternoon and evening. But you'll see that the title's changing at the top between packets and bytes. So this is just showing what this histogram looks like when you count bytes and when you count packets. You can see it really doesn't seem to change a lot. But if you look careful down there at the DSCP 24 and DSCP 32, they actually do move a decent amount, probably 50, 60%. That would be more visible again if the DSCP 0 bar wasn't so high, but interesting results anyway. Okay, so summarize a few things here. So, lastly, I guess looking at this, there is little difference in the distribution when counting packets or bytes. So I think from future analysis, I might not bother to count both, but it's really pretty simple to have separate counters. So it was just easy to do, but it really doesn't seem to change the histogram and the distribution very much. Okay, so a few observations and summaries. So most traffic is marked with DSCP. So what are the implications of this? I think we could have some interesting discussions about what that means for Wi-Fi prioritization and NQB and a bunch of really interesting things that are related to DSCP. For the non-DSCP zero traffic, of which it's not a lot, there is a lot of variation across these ISPs. They're all US regional providers. I doubt the user population is that different across them, although I have no way to prove that. So I suspect this is network configuration and equipment. We haven't had any time or have any really idea of what the cause of that would be. But it was definitely not nearly as consistent as I probably would have expected given the similarity of these ISPs. Afternoon traffic has a higher percentage of DSCP than the evening. That's kind of interesting. I guess that implies that the applications in the evening are more likely to mark. Maybe that's gaming. I'm not sure. And upstream traffic is much more consistent to DSCP distribution across all the providers and, of course, mostly to DSCP 0. So that's a few summarizations. Little note at the bottom here. If you're interested in protocols, there's this really cool thing happening with Blue Sky with this really interesting architecture. But more relevant to this is for a long time, I've wanted somewhere where I can follow network news a little bit more easily. And Blue Sky allows you to build these custom feed algorithms based on the fire hose of posts. So I just launched Network Nook, which is basically it filters all the Blue Sky posts looking for network terms because I'm hoping I can find interesting things. So if you'd find something like that interesting, you can search for that or just search for it on Blue Sky, and hopefully everyone else will get some use out of that as well. So with that, we will take questions.
Thank you very much, Dan. Let's do at least one question live. So Matt is asking, did you test all DSCP code points or just a few? And I think he's asking about, I think he's assuming you tested for bleaching. Is that right?
So what this is passive. So in all cases, I captured a bunch of data and just reported on what was seen on the network. I didn't introduce any traffic. I didn't test specific code points. It was grab all the packets, do counters for each of the 64 bins for DSCP, and then build a little pipeline for results after that. So yeah, I mean, those charts that show all the DSCP possible values in the bottom, that is all the DSCP
Okay, very good.
Picture.
So
yeah,
if there is bleaching of specific marks, those would just not show up.
They'll all be 0. That's right. Yeah. I'd have no way to know without capturing, I guess, at different places in the network or something to know if there is bleaching happening.
Yeah. And that answers one of the other questions as well, which is how do you know the DSCP marking is unchanged?
I don't. Yeah. So
yes.
This is like where this is capturing in all these networks is a location, kind of a centralized location, right? So generally slightly below the transit, depending on the ISP size, sometimes it's closer to the customer, sometimes it's more in the core, but it is a pretty central place. So if things are getting bleached and remarked, they're either probably coming from the transit side or else there's something, low in the network, like a CPE or something, maybe a router that's doing it.
All right. Thank you very much. I think that there may be more questions in the Q&A. So if you have time to look at that, that would be great. Thank you very much, Dan.
Thank you.
Our next speaker is Dr. William Webb. He's an independent consultant and author of many books, most recently about the end of telecoms history. I don't think that's the topic of this talk, but I wanted to include it in the introduction anyway. So please, William, share your screen and take the stage.
Thank you very much. Let me just bring my presentation up. Shouldn't take a moment.
I can see your presentation now.
Great. Thank you for that. Okay, so slightly higher level presentation than the last one, or much higher level. So I'm going to take a big step back and ask what's going on in 5G in terms of latency and where might we end up. So an important starting point is to go back to around 2017 when the community was setting out the expectations for 5G. And indeed, the ITU set out the formal requirements for 5G in a formal document that essentially says this is what 5G needs to achieve in order to be considered to be 5G, or IMT 2020, as they considered it in their parlance. And one of the key metrics, as you can see on the right-hand side of the hexagonal box structure, is 1 millisecond latency. And that was often touted as a big highlight for 5G. In fact, if you dig into the expectations, there was two latency numbers. There was the latency for general, what was called enhanced mobile broadband, EMBB traffic, which was 4 milliseconds. And then there was a different latency number for the ultra reliable and low latency service, or URLLC service, which was 1 millisecond. So that was what 5G set out to achieve. And indeed, it's still something that's talked about as people discuss 5G. They talk about achieving those kind of millisecond latency levels. And that's seen as important to deliver many of the applications that were envisaged for 5G, although, as we now know, haven't yet happened. So where are we with that? And where might we head to on that front? Well, in general, if we just look at all mobile, these are some speed test results I downloaded recently. You get something like 27, 30 milliseconds latency across most mobile networks across the world as an average. And that compares with something like 9 milliseconds for fixed broadband. So mobile is about 3 to 4 times worse than fixed in the 30 to 40 millisecond region, roughly. And that has come down a little over the 5G era. So 5G has improved things somewhat. Typically in 4G, we were looking roughly at 40 milliseconds. So things have improved from 40 to 30 roughly over that time. No bad deal, but no dramatic change to the way that we do things and think about things. And it's perfectly understandable, of course, that mobile is worse than fixed. It's a shared channel, and therefore you have to take the time to gain access to the channel. And that adds a whole load of extra delays into the process. And it has much more complexity in the way of overheads and control structure and so on than you get on fixed broadband. So none of that should be any sort of a surprise to us. Well, one thing that 5G needs to do if it's going to deliver its low latency is it needs to move to a 5G core. And that's sometimes called 5G standalone. So 5G can be deployed in two approaches. What's called non-standalone NSA, where 5G makes use of the 4G core. So all that you deploy is the 5G radio access network, or RAN, but you stick to the existing 4G core. Or there's 5G standalone, 5G SA, where you put in a dedicated 5G core. And because many of the delays occur in the core, and 5G SA or 5G cores are optimized for low latency, then if you really want to get down to anything significantly better than 4G latency, then you have to have an SA core. Well, you can see from the chart here that there is some progress on that, but it's not been fantastic. So if we go back to 2021, we had 82 standalone networks and 453 non-standalone networks. Now we've gone up to 617 non-standalone and 143 standalone. So gradual improvement in percentage of standalone, but not enormous, which suggests that it's going to take quite a long time for us to get to everyone using standalone. And indeed, perhaps we won't. Perhaps we'll plateau out at some level below that, because operators are concluding often that moving to standalone is quite expensive, it's quite risky, and there's no clear benefits for them to do that. So already we're in a situation where an awful lot of the 5G networks out there are just not capable of delivering anything better than about 30 millisecond latency, because they don't have the core that would be needed to do that. But even where they have deployed the core, for example, T-Mobile in the US has got standalone, it doesn't necessarily mean that they'll drop in latency. And indeed, in T-Mobile's case, they have slightly better latency than other US networks, 47 milliseconds versus 55. The other ones are non-standalone, but moving to standalone hasn't in their case made an obvious difference, because they haven't adopted some of the other configurations that are needed to get down to that low level of latency. So that's one of the key issues in achieving low latency. But perhaps more importantly, it's not clear that we need it. So this is a blog from Ericsson from 2022, who were one of the key proponents of the very low latency in 5G and set out many reasons why it might be needed. But in this blog, they essentially say, if you're somewhere in the region of 30 to 50 milliseconds, then that's absolutely fine for people. Even gamers find 30 milliseconds absolutely fine. Perhaps there might be one or two superhumans for whom 20 milliseconds might make a slight improvement, but beyond that, absolutely not. And of course, most of the users of mobile networks are people. So from that, you might deduce actually one of the reasons operators aren't moving more quickly towards lower latency is because there's no clear need for it, at least not whilst they're connecting people. And we'll come back to machines shortly. But another reason is the sheer cost of delivering latency, low latency. So this is a chart from an academic paper. You can see the reference there. And it shows how much standard network traffic, EMBB traffic, you give up when you have a certain amount of low latency URLLC traffic. And it shows it for two different block sizes, 32-byte block sizes and 200-byte block sizes. If we take the worst case of the small block sizes, which is where you get the lowest latency, then essentially the line shows you that it's got a gradient of minus 58.9, which suggests that effectively, roughly, there's a 60-to-1 penalty for using low latency. So if you have 1 megabit a second of ultra low latency traffic, it displaces 60 megabits per second of standard broadband traffic. If you move to bigger block sizes, then the penalty is tenfold. So we're somewhere in that region of 10 to 60-fold penalty for delivering ultra low latency traffic. And that's because essentially we have to leave a whole load of spare slots ready for low latency traffic so that it doesn't have to wait for the carousel of slots to come round and it find a spare slot within it. And leaving those slots spare clearly has a cost associated with it. So if you're going to deliver low latency, you'd want to be pretty sure that you are going to get more revenue to compensate you for the loss of capacity of broadband traffic that you can sell at the moment to existing consumers. And that's clearly going to be a significant detriment or disadvantage for mobile operators who choose to go down that particular path. Well, I mentioned machines earlier, and certainly you can envisage machines that might want lower latency than people. And that's led a number of people to suggest that actually what the low latency service is really for is for machines, for robots on factory lines or things like that would benefit from the low latency. And that's certainly a possibility. So you can imagine in a private network set up, let's say on an assembly line, that you might have machines that need that low latency. And it might be the case that you don't worry about the loss of capacity because you've got plenty of capacity in your factory. So giving up some of the base capacity for low latency isn't an issue. But even then, what we see in this chart is a whole load of measurements that were taken on a private network, and they show a latency of around 10 milliseconds. Now, that's a lot better than 30, but still nowhere near the 1 that was promised. And one of the key reasons for that is because most private networks make use of spectrum that's allocated in typically the 3.8 to 4.2 gigahertz band. And that spectrum is TDD, time division duplex, with a 10 millisecond frame repeat. So essentially, you have to wait for the frame to come round once in order to be absolutely certain of getting an uplink and a downlink slot. Now, in some cases, you won't need to wait that long. And that's the reason why some of the latencies are a little below 10 milliseconds. But that's kind of be your anchor point, roughly, that it's going to be very tough to go much below that. Now, you could potentially get some frequency division duplex spectrum allocated, but there's not much sign of that at the moment. So it feels that it's going to be unlikely that in practical private network deployments, we're going to see much improvement below the 10 milliseconds. And it's not clear there's many of these, actually. There may be a few hundred around the world, maybe 1,000, but we're talking relatively low numbers. This is not mainstream 5G. So, conclusion from all of that, it seems unlikely that we're going to see significantly lower latencies in public networks, both because there's a very high penalty for the operator in doing so, in giving up network resources. And because there's no clear demand for it, because people generally don't see significant improvements in below 30 millisecond latency. And even if neither of those were true, we'd still need standalone core deployed for 5G. And that's slow, it's stalling, and it's not clear that that's going to pick back up again. It's possible that there's value in private 5G networks, but those are relatively small. And indeed, where they need really low latency, it's not clear that 5G can deliver it because of the TDD framing structure and timing. And indeed, maybe Wi-Fi fixed networks or some kind of proprietary technology might be a better solution for that. So it's not necessarily bad news. It's just that 5G is not going to be the place where you're going to get the 1 millisecond latency. 5G is doing just fine delivering what people actually want, but it's not the low latency place to go. I'll leave you with one last thought. These are the targets for 6G, which are now published in draft form from the ITU. And they suggest that the 6G target for latency should in fact be 0.1 milliseconds. Make of that what you might, given that where we're at with 5G at the moment. And that brings me to the end. Thank you very much. Hopefully we've got time for a few questions.
Thank you very much, William. It's very interesting stuff. Kevin Smith is asking in the chat, just one use case I can think of humans needing sub 30 millisecond is live audio.
Yes,
thoughts on that?
That has been a potential use case for 5G, and indeed there has been a number of sort of demonstrations of orchestras in different parts of the world playing together through having very low latency. I mean, it's a corner case effectively. It's not a big case, and often it's achieved through either special equipment, PMSE type equipment or similar. So I don't think it will be enough to drive operators to want to effectively move to a much lower latency in their network. So I think it's that's right. It is a case, but it's not perhaps enough of a driver to deliver this, and it can probably be delivered through other technologies.
All right.
I'm just looking at some of the other chat comments. Yes, I think I agree with many of those.
I like your quote on the next to last slides. It would be so nice if something made sense for a change.
Yeah. It can feel like that at times.
It would be nice, wouldn't it?
Yeah.
Yeah, Vivid is asking in the Q&A tool, how do you expect 5G broadband to effectively compete against fixed broadband from a latency perspective?
Yeah, I don't think it will. So fixed broadband is delivering routinely less than 10 milliseconds latency without any trouble whatsoever. 5G, as I said, I don't think it's going to get much below 30. So if low latency is important to you, then use fixed broadband. And indeed, some of the applications that have been put forward where low latency might be important, like metaverse type applications using a VR headset, are naturally indoor applications that run over Wi-Fi and therefore fixed broadband anyway. So it feels that essentially there's a fairly good match between the potential need for low latency applications and fixed broadband versus much less need for 5G applications. But I do think that means that 5G won't displace fixed broadband for most users. I know that it does in some cases for fixed wireless access, but for many, I think home broadband is a better solution.
All right. Thank you very much, William. That is everything we have for today. Before we end the call, I just want to remind you all about the agenda for tomorrow. So tomorrow, Dave Todd is talking about LibreQOS. Greg White from Cable Labs talking about NQB, non-queue building, which is a DSCP marking RFC. Stuart Cheshire from Apple is talking about buffer management in the sources. Neil Cardwell is talking about BBR. It's a congestion control algorithm from Google. Christian Anderson from Ericsson is talking about 5G and latency. explained, and then Simon Sundberg from Karlstad University is talking about measuring network latency from a wireless ISP. And so I hope many of you join us tomorrow, and thank you all for joining us today. And I also want to say thank you very much to all of the presenters who has spent time with us and share their knowledge. We very much appreciate that you're taking the time, and thank you very, very much. So see you tomorrow, guys.